Hi everyone, welcome to the Precalculus Chapter 1 Part 1 review. We're going to cover sections 1.1 to 1.4 to prepare you for your exam. But first, if you want to view these notes that you see here, just go to the website, click on the link to view and download them. So at champscharter.org, you can go ahead and search for my name, and then we're going to go ahead and find our class under Precalculus. And then there is an announcement/assignment posted for you to watch this video. And at the bottom, you'll see a link right here. If you click on that, that's going to bring you to the slides that I'll be using in this video to present the review. If you want to navigate through this, there is a tab on the left-hand side where you can navigate through 1.1, 1.2, 1.3, and then 1.4 I'm not going to review because we've already done a pretty thorough review in class. But these PDF attachments are here, and those are also posted on the website. So, without further ado, let's begin. I want to remind you that we have a few graphing calculator skills that we absolutely need to have for this test. We should be able to graph a function by going to y equals on our graphing device. We should also be able to zoom in and out to observe a certain point that we're interested in on the graph of the function. We should be able to identify and view our table of values, and we should also be able to calculate exactly our maximum and minimum values using our graphing calculator. So starting with section 1.1, this is a quick overview from Algebra 1 and Algebra 2 about lines and linear equations. First and foremost, the slope of a line is the rate of change between 2 points. And remember, we represent the slope with this lowercase m. And this change in y over change in x can also be represented with the notation delta y over delta x. That's less important. It's more important that you understand what it is, which is the difference between y values divided by the difference between the x values. Okay, also really important to note, parallel lines have the same slope. Remember that parallel lines are simply two lines that run in the same direction at the same rate of change. So therefore, they would have the same slope. Perpendicular lines, however, would be ones that intersect at 90 degrees and do not run in the same direction at the same rate of change. In fact, their slopes are the opposite reciprocal. Really important to note that. There are three ways that we write the equations of a line. So these forms are the general form, the slope-intercept form, and the point-slope form. General form, I'm not that interested in, but it is a nice, neat way that we can write the equation of a line. That is ax plus by plus c equals 0, where a, b, and c are all simply integer coefficients. The slope-intercept form and the point-slope form are the two that are the most helpful in terms of graphing a line. So the slope-intercept form is the one you're most familiar with. That's y equals mx plus b. The slope is the m, and the b represents the y-intercept of this graph. So just as a quick example, we could take a look at the equation y equals, let's say, negative 2/3 x plus 1. The slope here is negative 2/3. That's the rate of change between each point. The y-intercept is up at 1. So if we were to do a quick sketch of this, we can go ahead and start by plotting that y-intercept point up at 1. And then our rate of change down to over 3. Now that we have those 2 points, we can simply connect them, and there's our line. Okay, point-slope form is y minus y1 equals m times x minus x1. So what do all these pieces represent? Well, this y1 and this x1 are simply x and y values from a point that exists on the line, and the m is still representing our slope. So a quick example here, if I wanted to write the equation of a line, and I was given a point, let's say 1, 3, and I was given a slope, let's say 2/3, and I wanted to go ahead and write the equation that represented the line that had that information. I would say y minus, well, the y value here is 3, so I'm going to go ahead and put in 3, equals m, my slope, which is 2/3, times x minus my x-coordinate of the point, which in this case is 1. If I wanted to clean this up and put it in any of these two forms, general form or slope-intercept form, I could do that just by manipulating things and rearranging some of the variables. Typically, we would put this in slope-intercept form by isolating the y. So we can do that. Let's distribute this 2/3, and we get y minus 3 equals 2/3 x minus 2/3. Now I'm going to add 3 to both sides, and we get y equals 2/3 x, and now we have to add negative 2/3 plus 3. In order to do this, I'm going to think off to the side, how can I add negative 2/3 to 3? Well, first I would want to convert this positive 3 into a fraction out of 3, which would be 9/3. So we have negative 2/3 plus 9/3, which is just 3. So now that I have this common denominator, I can go ahead and do 9 plus negative 2, which is simply 9 minus 2, or 7/3. Okay, so there you have it. That's the equation of the line given this information. Let's move on to section 1.2. Functions. There was a whole lot of information about functions. First and foremost, the notation that you've learned is f of x. We read this as a function of x. What this means is x is our input, while f of x represents y, or the output. The test for functions is to determine whether or not for every single input there is only one output. So remember the vending machine example. How can you check if something is a function? We're going to do two different examples here to see if something is indeed a function just algebraically, not by looking at the picture of the functions. So I'm going to go ahead and take 2x plus 3y equals 4. And I want to know, is this a function? Well, first of all, this is kind of sort of written in that general form of a linear equation. So I might think maybe it's a line. But let's algebraically check if I can isolate the y. That's the goal. If you can solve for y and isolate it, then it is indeed a function of x. So I'm going to go ahead and try to isolate this y. So first I'll subtract 2x, and then I get 3y equals negative 2x plus 4. And now I'll divide both sides by 3, and I get y equals negative 2/3 x plus 4/3. I've isolated the y to the left-hand side. There's no other y's on the right-hand side of this equal sign. Therefore, I can rewrite this. Instead of using y, I can go ahead and use that function notation equals negative 2/3 x plus 4/3. So this one is indeed a function. Okay, let's look at a different example. Suppose I have the equation x squared plus y squared equals 4. Now remember, the goal is to try and isolate the y. If I'm trying to isolate the y, I'm trying to get this y all by itself. So let's first subtract the x squared. I get y squared equals negative x squared plus 4. And now if I want to get y alone, I have to take the square root of both sides. But in doing that, remember with the square root, we have both a positive and a negative result. So when I do this, I get y equals positive square root of negative x squared plus 4. And we get that y equals the negative square root of negative x squared plus 4. And if we graphed both of these separately in our calculators and put it together, The upper half would be this semicircle, and the bottom half would be this semicircle. And together we're going to discuss how that would not represent a function graphically. It does not pass the vertical line test. So speaking of that vertical line test, if you're looking at a function and you draw a vertical line, if you're looking at the graph of a function, to be more specific, and you draw a vertical line anywhere, you should not be able to pass through more than one point if it is in fact a function. In this particular example, we pass through 2 points. Therefore, this would not be a function. Remember, for every input, there must only be one output. Let's move on to evaluating functions. Just a quick example. Let's suppose you were given f of x equals x squared minus 3. If I want to evaluate f of 2, I'm going to replace x with 2. So this results in 1. If I want to evaluate f of, let's say for instance, h plus 3, that means wherever I see an x in my original function f of x, I have to replace it with h plus 3. So now I have h plus 3 squared minus 3. To simplify this, I do have to distribute and FOIL, and I get h squared plus 6h plus 9 minus 3. 9 minus 3 gives me 6. So I get h squared plus 6h plus 6. The difference quotient is simply a formula that is going to be of great use to us later on and if you study calculus. Alright, so let's see an example of how to simplify a function in the difference quotient. So if I were to give you the following function, and I wanted you to simplify the difference quotient using that function, I would go ahead and use this little formula and do my evaluation. So what is f of x plus h? Well, I'm going to go ahead and put x plus h in for my x. So let's do that. We would get 2 times x plus h squared, and then minus f of x. Well, that's simply f of x. F of x is 2x squared. So I'm going to go ahead and write minus 2x squared, and then all divided by h. Okay, so from here you would clean it up by distributing the x plus h times x plus h. So we would have 2 times x squared plus 2xh plus h squared minus 2x squared all over h. Simplifying again, we're going to distribute this 2. And I'm going to bring it down here. We get 2x squared plus 4xh plus 2h squared minus 2x squared all over h. Notice 2x squared minus 2x squared, that's 0, those cancel out. And I'm left with 4xh plus 2h squared. I can factor out an h. And I get 4x plus 2h all divided by h. Now I can just cancel these h's, and my final answer with the simplified difference quotient would be 4x plus 2h. All right, let's discuss the domain and how you identify a domain algebraically. So the important thing is you should know your restrictions with functions. We have rational functions, and those have a restriction that the denominator cannot be 0. For example, suppose I have 1 over x minus 7. I know that x minus 7 cannot equal 0 because that would make my function undefined. That's a restriction. Therefore, x cannot equal 7. But x can be everything else other than 7. So to write my domain for this one, I would list everything from negative infinity to infinity with the exception of 7. So we would say negative infinity to 7. I'm not going to include 7, but then I'll continue that with my union from 7 on to positive infinity. Another way of writing this is all real numbers except for 7. Another restriction we learned about is with radical functions. Suppose we have y equals the square root of x minus 7. My restriction here is that x minus 7 can't be negative. Therefore, it has to be greater than or equal to 0, which means my x's have to be all greater than or equal to 7. So my domain in this example would be all real numbers that are greater than or equal to 7. And we notate that with our brackets. So everything from 7 to infinity. Okay, also in section 1.2, we discussed how to evaluate piecewise functions. So if we're given a function, for example, f of x equals these two pieces, 3x squared plus 1 and 2x minus 4. Suppose that this first piece is defined only when the values of x are less than or equal to 0. And then suppose this second piece is defined for all other values greater than 0. If I asked you to evaluate f of -1, for instance, you would have to use this first piece since -1 is a number less than 0. Since -1 is less than 0, I'm going to put -1 in for this first piece of the piecewise function. So we get 3 times -1 squared plus 1, which is 3 plus 1, 4. If I wanted to evaluate f of +1, I'm going to go ahead and put that in my second piece because +1 is greater than 0. So when I put that 1 in for my x in the second piece, I get 2 times 1 minus 4, 2 minus 4, which is -2. All right, let's move on to section 1.3 and summarize how we looked at the graphs of functions. First and foremost, you should know the difference between increasing intervals, decreasing intervals, and constant intervals. Intervals of increase are anything from left to right that have a positive general slope. Decreasing are intervals on a graph that have a general negative slope. And intervals where the graph would be considered constant would be where we have a slope of 0. When we discuss relative extrema, that's simply where our relative maximums and relative minimums. So remember that a maximum is simply the top point of a mountain or a hill. It is the point where our graph changes from increasing to decreasing. It's that exact moment where we have that change from increasing to decreasing. On the flip side, a minimum is the bottom of a valley where we have that change from decreasing to increasing. It's that exact point where we're changing. You can have multiple maxes or mins on one graph. So just make sure if you were looking at a picture of a graph, you could point out all of the maximums and minimums. In this case, I have two maximums, relative maximums, where there's 1, there's 2. I have a couple of relative minimums down here. And you should be able to identify where those points are on your graphing calculator. Domain and range, remember the key is that the domain values are all of the x values, and you read domain from left to right. That is the most important thing. You read domain from left to right as you go from left to right reading your graph. You go from left to right. All of the yellow is all of the bases I'm covering in my domain for the function. So remember, domain are the x values, and we go from left to right. The range, on the other hand, are all of the y values of the function. And we read all of the y values from bottom to top. So you're going to read those from bottom to top when we're writing this in interval notation. So from bottom to top, as we go along this curve, we see what y values are being covered. Okay, the next part of 1.3 was how do we graph a piecewise function? Well, remember, a piecewise function is simply two different pieces with defined domains. So let's look at two different pieces. For example, y equals, let's just say x, very basic. And let's just say the second piece is x squared. Let's say we have the line x for all values greater than or equal to 2. And let's say we have the piece x squared for all values less than 2. How would we put this together on a graph? I want you to think that everything greater than or equal to 2 means everything to the right of 2 or equal to 2. Everything less than 2 would be everything to the left of 2. You know that the line y equals x is simply going to be this line going through 0 with a slope of 1. So for this piecewise function, that piece I'm going to sketch is only the piece starting at positive 2. So I'm going to go over to positive 2, up 2, and I'm going to draw the graph with a closed circle to include the 2. And I'm going to carry on in the positive direction for all values greater than 2. So that green piece right there, that's the piece that I want to keep for everything to the right of 2 and equal to 2. So I'm going to get rid of the rest of that line because that's not part of our picture. So now let's do the second part. The second part is the graph x squared, which you know is a parabola at 0, 0, and it looks something like this. But I'm not concerned about any of those values to the right of 2. I'm only concerned about the values to the left of 2. But I do need to figure out what is my output at 2. What would the output be at 2? So if I were to plug in 2, I would get 4. So this would have a value of 4 at x equals 2. So I'm going to graph that point, but when I do that, I'm not going to draw a filled in circle. I'm going to draw an open circle because that's going to represent that I'm not including the number 2. So I'm going to go over 2, up 4, and I'm going to sketch an open circle. This is going to indicate that we're not including that point, but we're going to that point. Now I simply connect, I'm going to connect everything else in my parabola below that. And this arrow over here indicates it does go on forever, upward and to the left. Okay. Okay, testing if a function is even or odd. We know that we learned even is when a function is symmetric about the y-axis, and odd is when a function is symmetric about the origin. How do we test if something is even or odd? Well, if we substitute in negative x and simplify, and the result is the same as the original function, then it's even. If we substitute in negative x and the result is the exact opposite sign of the original function, then it's odd. If neither of those two cases work, then it's neither even nor odd. All right, everyone, I hope you enjoyed the review from sections 1.1 to 1.3. I know it was a little bit long-winded. For 1.4, please go ahead and refer to your notes and in-class investigation. If you'd like a little more practice, you can go to page 88 in your textbook and attempt problems 1 to 15 with the exception of number 6. So in interval notation, everyone, that would be problems 1 to 6, not including 6, union problem number 6 to 15. So you don't have to worry about problem number 6, but I would like you to try all the others between 1 and 15 to prepare for your test. I hope you enjoyed the video. Thanks.